Welcome back, everyone. I hope you had a good lunch break. Before anything else, I remember someone asked about fixed balance and whether or not it could be used with GPUs. I can confirm that it cannot. You can use balance, you cannot use fixed balance at this point, or at least with the version of LAMMPS that I tried. Hopefully the LAMMPS developers will change that in the future, as they're always improving the number of things that are compatible with the GPU acceleration. So I forget exactly who asked that, but I'd like to let you know that. I've also updated the GitHub with all the exercise files should now have the correct budget for TA132. And I've also added a fifth exercise for some GPU acceleration that we can take a look at the end of the session. Does anyone have any questions from the stuff we did this morning? Guess there's no questions. So I'll be sharing my screen and we can have a look at replica exchange. Right, so I remember someone was interested in replica exchange. I will apologize in advance. I've never actually done any research or any simulations using this. I'm using material created by Stephen Farr, which was a EPCC employee. This course was delivered last year as well. So any mistakes are mine and not his. As far as I know, this is mainly used in biomoleculars, or largely used in biomolecular simulations, although it can be used with other polymers or long molecules that might be hard to simulate all the different conformations. So if you imagine a potential energy a surface like this, and you'd like to probe all of the minima of configurations of a large polymer, scale of simulations. The idea here is that you can temporarily increase the energy of a certain system so that it goes to a higher temperature, so that you can change its conformation and then bring it back down again so that it hopefully falls in different local minima or even the global minimum. With replica exchange in LAMMPS, what you can do is instead of simulating one system and changing the temperature around, you can simulate 10 different replicas of the same system at the same time, each at a different temperature, and then using metropolis exchange criteria like it's used in Monte Carlo to swap the temperature around of each system so that they can all explore the entirety of the temperature range. And here the criteria for exchanging a temperature, so the probability depends on the temperature of each system, of each replica, and the energy of each replica. And to my knowledge, the best recommendations are that you have a probability that is around 30%, so that you have a good exploration of the entire space. Exercise 3 is one such system, and we can have a go at it. It is a very simple toy-like system, which consists only of a linear polymer with 50 beads, and it will create 10 different replicas of the same system at 10 different temperatures. So I will follow this one with you. So if we take a look at the input file for LAMMPS, the two major differences here are these world variables. These are the variables that will be used to generate the different replicas. Here, each variable has 10 different values. So we've got from 0 to 9. This is just a replica identifier. And here we have the temperature. It goes from 300 to 1,000 with some steps in it. And basically, at the beginning of the simulation, replica 0 will be assigned to 300, 1 to 354, etc. And the other thing is that instead of a run command, we use the temper command. Now, LAMMPS needs to be compiled with the correct packages for these to be available. The module we have installed on ARCHER2 right now includes this. If you have a local installation, you might need to do a new one to add the correct package. I believe it's called replica, but that might be wrong. The way we fix the we fix the temperatures for each replica is by using the world variables up top. You give it the variable, and for each replica, it will choose the correct index, basically. So it will do replica index 0, will do T index 0, and I index 0, so that it matches all of that. So for the dump here, it will create 10 different trajectory files one for each replica. Now, if we run this, invalid account. Did I not change this one? No, I didn't pull here. Okay. I think this takes a couple of minutes to run the nanosecond, I believe it is, or million time steps. We can speak a little bit about choosing the temperature scale. Oh, that was good. So I believe the temperature scale is something that that is going to depend a lot on the size of the polymer and if you have solvent, the number of particles in the course materials online generator for the temperature ranges and the publication in the source code. But you might have to experiment a little bit with your system to make sure that it matches. The other thing that you need to change to run a simulation like this, and I forgot to show you, is on the Slurm simulation. You need to add this keyword here, partition. And we're doing 10 replicas, the first number before the X, 10 replicas, X, and the number of cores per replica. So this is such a small system that we're just using the one core per replica. So we're using 10 nodes, but on larger systems, you want to be using more than this. So if we have a look at the output, what the system has done here then, or what LAMMPS has done here, is that it starts on step 0. We see here which temperature each replica is using. So on step 0, replica 0 has temperature 0, replica 1 has temperature 1, so on and so forth. And as things move, we have told LAMMPS to use that probability chance of swapping temperatures around between the replicas. So you can see here at time step 100, replicas 1 and 0 have swapped temperatures. So replica 0 now has a higher temperature, and replica 1 now has a lower temperature. And this keeps happening every 100 time steps. The temperature is changed, and of course you can vary that for your system. And here we have a list of all of the changes that happened. Now this isn't very useful in terms of in terms of having a trajectory for one replica, we will have then to fix that, and we have some scripts to help us with that. But the first thing we should have a look at is checking that our probability of changing is around 30%, at least for the lower temperatures. So we can do that by using one of the Python scripts we have, which is this one. Before that, I need to load the create Python module. Otherwise, I won't be able to run any Python. If we do this, we get the results. So the acceptance ratio for each pair, basically, it starts around 30%, but because our system is so small, at higher temperatures, this acceptance is much higher. But that's basically an artifact of having such a small example system. For larger systems, this should be a little bit more flat in terms of the acceptance. We can also make sure that our systems are traversing the temperatures in an appropriate manner, and you can do that with GNU-plot by plotting the temperatures. We can see here an example of a good traversal, which is what ours should look like, and a poor traversal, which was calculated by increasing the number of, by decreasing the frequency at which temperatures swap, basically. So here, a good traversal, we see that, I believe this is for replica 0. It went to max and minimum temperatures several times during our entire simulation. So it traversed the list of temperatures fairly well. Now, we now have a bunch of trajectories, as you can see here. We have a different trajectory file for each of the replicas. But these trajectories are not at a constant temperature. So each replica will be moving around in temperature up and down, and that's not very useful. So the next thing we can do is order them, or reorganize them, I should say. And for that, we have this script here. So, sorry, I'm skipping things. The reorder command is here. Reorder, that's the one. And I believe it needs the prefix, so what comes before the number, then the number of replicas. There we go. So this created even more files. So now we have the original ones where each trajectory is a replica, but the temperature keeps changing. And now we have 10 different trajectories for the same temperature. So each trajectory now is at a constant temperature. So we can now analyze those trajectories, those constant temperature trajectories. And in this case, we're going to use a rerun like we did on the previous section. And we'll be calculating an histogram of the radius of gyration here. Yeah. This is a LAMMPS command to calculate the radius of gyration. The radius of gyration is basically size/shape of a polymer. It gives you an approximation of how the radius of a spheroid polymer is, but if your polymer is not exactly a spheroid, the number might not make a lot of sense. So here we'll be rerunning from the temperature, constant temperature trajectories from the folder we had. And again, we have a world index variable for the 10 different replicas, so that we calculate these for all of the replicas. And I believe we have a run.slurm. Is it rerun.slurm? It is rerun.slurm. And of course, this hasn't been changed. So this shouldn't take long because again, it's post-processing. It should be fairly quick. So let's see if I've got gnplot. I do. So we can just use the scripting, the gnplot script that has created that plots all of the temperatures at the same time. And here we can see that as we increase the temperature, the radius of gyration gets larger, and also the range of values that it can occupy increases. So here, this is the lowest temperature, this peak here, and it's fairly narrow peak and at lower size as well. So that's expected, and I think I've got some pictures on the course material that show this. Yeah, there we go. At lower temperature, you'll have a polymer that's much more compact, globular spheroid, if you will. And at higher temperatures, you'll have something that's much more elongated and much more spread about. That's why you get a larger radius of gyration, but you also get more movement, more change at higher temperature. So there is much more variance in the ranges of radius of gyration that they can occupy. There's links here for papers on how to do replica tempering, as well as the LAMMPS documentation on this. I'd say to give it a go. If you can follow the all the instructions are here in the course material. If you didn't follow what I was doing, give it a go. See if it works for you. And if you have any questions about this, I'll try and answer them. Something that I think I touched, but I think I should maybe reiterate, is that here you can run each replica with more than one course, so you'd have to increase the number here at the end after the X. But you also would need to increase the number of tasks per node here. Or if you want to use an OpenMP rather than more MPI tasks, you'd increase CPUs per task. That's also an option. Is there any questions about this part? Okay. Yeah, sure. Ask questions, Carlos, even if it's not about this part. I'll say I'll give you 10 minutes to run these exercise on the replicas. So the question is, are there specific cores for post-processing in ARCHER2? If you want to do something serially, as in just use the one core for post-processing, there is the serial rotation. I don't know the details off the top of my head, but if you go to the documentation and you search for partitions, all the information will be here. So we have the serial ones. There are only 2 nodes, and you can only request 1 core per job that you submit to the serial queue. There might be some restrictions on what they can access, but as far as I remember, they should be able to access both the file system and the modules that the standard cores can. So you also need to use the serial QoS as well. So the restrictions are here. The jobs are not charged, but you need to have a positive budget. Yeah, there's limits on how much you can, any one user can use at each time. So yes, if it's something quick, you can you can, and by quick I mean like 2-3 minutes. You can just launch it on a login node. If it's something that's going to take a little bit more, yeah, just use the serial nodes for that data processing. If you need more than one core, unfortunately, I think you'll have to use budget for it. Is that what you were after, Carlos? Raise your hand once you're done with the exercise, so I can have an idea. No, Andres, that is basically the end of the exercise. So by that point, you have the 10 replicas. So the simulation of the 10 replicas, you have the trajectory files of the ordered or the reorganized by temperature. And by that point, you rerun a calculation of the radius of gyration on those reordered so that you have your distribution of radius of gyration versus temperature. So that is pretty much the end of the exercise. Is anyone still finishing anything? Otherwise, I think we can continue. Okay, Robin, unrelated question. Are we able to run a different version of LAMMPS on Archer? If we have written a custom fix, for example, not included in a modular version? Absolutely, you'll have to compile it yourself, and that's what we'll discuss a little bit about now. Yeah, I can just jump into this. So here I'm giving you, or I'm showing the instructions that I used to compile the LAMMPS version of the module that we'll be using today. So if I show you here, we'll be now loading the LAMMPS Python wrappers around it. So it loads this version of LAMMPS as a dependency, and then loads the Python wrappers around it. But if you're using your own, yeah, you just need to add LAMMPS to your path, or you can just call the full path rather than just LMP. And as long as the compiled binary is in the work file system, then you'll be able to access it from the compute nodes. So all of the instructions for all of the central modules that we have are on HPC UK GitHub, as well as other packages for other systems. So as you can see here, there's some for Cirrus, which is our tier 2 as well. I'll get you a question in a bit, Thomas. So this is the direct link to the 15 December version. So all the instructions basically for how it was compiled are here. Sometimes there are a few rationale that are not exactly included, as why some packages are included, why some others aren't. Usually we try to include everything that does not conflict, and that doesn't include any extra libraries that we don't have accessible on LAMMPS. So in this case, this module was compiled with the preset most that comes from Sandia, from the LAMMPS developers, and that includes pretty much any package that doesn't depend on external libraries that are not included with LAMMPS. So if we run, I believe is this just -h, you get the help for LAMMPS, and somewhere in here it will tell you all the details of how it was compiled and when, as well as what compression formats are compatible, what the installed packages are. So this is what if you want to know whether some command is available or not, you can either search for the package here, or you can then search for all the atom pair styles, whatever you're interested in. They're all listed on the help of LAMMPS. So it's really nice that way. So if we go up, we can see that replica, which was needed for our previous one, and we have pretty much everything that is not dependent on some external stuff. Although there seems to be some ML stuff here that I'm not 100% sure whether they will be working 100% or whether you need to download some external data from that. Importantly, OpenMP, so that you can have those hybrid MPI OpenMP runs, as well as all the regular stuff like case space and molecule and OPT, many-body, all that stuff like that. Importantly, there's no GPU. GPU nodes have now been installed in ARCHER2. There's only 2 nodes. They're basically for testing purposes only. I'll be having a look as soon as we get access to those to see whether LAMMPS runs properly on it, if we need to change something on our compilation strategy or what else, but I still have no information on that. We do have on our tier 2 series, we do have GPU versions of LAMMPS installed. So series has both CPU and GPU nodes. So if you have an account there, you can run LAMMPS with the GPU acceleration. I can show you here. That is not the correct one. You see, there's LAMMPS and there's LAMMPS-GPU for GPU enabled code simulations. Let me go back to the compilation and explain a little bit about this. So, like I said, all the instructions we use are on GitHub, not just for LAMMPS, but for all the modules we use. So if you want to change anything, with apps to your needs, or install it on your local cluster, you might be able to find something that is at least a starting point for what you need to do for each package. The first thing you need to do when you're trying to compile is load the correct environment. In this case, I'm loading the Cray programming environment. On ARCHER2, we also have tested the differences using one or the other were fairly small, with a slight advantage for CPE. Sometimes these changes depending exactly on which version of GCC or AOCC is available with each programming environment. But this version was compiled with CPE. We're also loading FFTW, so fastest Fourier transfer in the West. So this is a scientific library written in Fortran, I believe, that is very quick at calculating Fourier transfers that LAMMPS uses. CMake creates the make files that are then used to compile all of LAMMPS. Again, I believe this is another auxiliary library, and Cray Python, because I was installing the Python wrappers as well. You then need to add the Cray scientific library path to the dynamic library path. This is just a step that needs to be done in ARCHER2. If you're doing your own compilation, you should also need to do this. If you're doing the Python environment, my advice is to create a virtual environment so that you can then load only when you need to run this. Otherwise, you don't need to be polluting your environment and mixing up packages and everything like that. The -- system packages, system side packages flag means that any Python package that is installed on the system environment on the Cray Python is used, and only if those aren't, only if a package isn't available there, then it's installed by grabbing it with PyPy or something like that. This is important because ARCHER2 uses modified versions of certain popular packages, like, I might be forgetting some, but MPI4Py, NumPy, SciPy, they are all installed centrally by HPE, and they've been modified to work better on ARCHER2. So even if you're doing Python development on something that's not LAMMPS, I would advise you to use this strategy to create a virtual environment. So the next step, I think I missed a Git clone here somewhere, but if we see here, you grab the stable you want, and you can change that to whatever branch you want, or if you have your own developed version, like I think Robin was asking, then you can use that. Yeah, Xenia, that is correct. So this was for the central installed version. So you'd have to change this path and that path to something that you have access to. So here I'm just showing up the instructions I used for the central installed version. So you go to your clone repo, you create a build directory so that every file that gets created and linked and compiled doesn't pollute the root folder of the repository. And then CMake is where most of the magic happens. It used to be the case that you had to edit make files manually depending on what you were trying to do. But a few years ago, the LAMMPS developers spent, in my opinion, a very well spent amount of time making a CMake file that is one of the best I've seen, or the CMake process is one of the best I've seen. You can indicate packages individually, or you can use one of the presets they have. There's a minimal, I believe, as well. And you can read all about it in the LAMMPS manual. With most, it will, I think, like I said, I think it installs everything that doesn't depend on other libraries. So you should be fine with most, unless you want to keep your compilation minimal for some reason. And then you have some options, some of which are because we're running on ARCHER2, and in other systems you might have something different. Others are because of the stuff we're compiling. So if you want to enable parallelism MPI, you need this flag to be on. The build shared libs is for the Python wrappers. So if you don't care about that, you don't need to install these. These two flags are for ARCHER2. So this just sets the C++ compiler to the CC wrapper. Other systems might use different. If you're using GNU, these might be different. And this is just new. This is where you want your binaries and your library files, shared object files to go after your installation is done. Again, this is a central installation, so it's in work/bio7. For your own case, you do work/ your project ID / your project ID / whatever you want. This is the directory for eigen3. This is where it's installed. So if you load the module, you should get access to these. So this one you should keep the same. And then this is the options for the fast Fourier transform library. So these ones you shouldn't be able to change, shouldn't need to change as well. And then we're just adding MPIIO package because we have MPIIO capabilities on ARCHER2, and this is not part of the default preset. And then you just tell CMake where its root files are, which is in the root of the repository /CMake. This will create the make files, and we can have we have time. I can show you how this works. So I'm going to need to copy this. So I don't know if you're not used to Git. Depth 1 just reduces the amount of stuff that Git downloads. And this branch, you could just have stable, which defaults to the latest stable, or you could specify a specific version here. And you can find which versions are available on the LAMMPS GitHub. If you go to here releases. This tag here will be the tag you need to do for whatever version you want to do. Or if you have your own repo, you can clone that. Okay, so then that I'm going to need to load some modules. You'll forgive me if I don't do the Python one here because it takes a bit longer than the version without Python wrappers. So if we go to LAMMPS, create a folder that's empty, and now not going to work, is it? Okay. Do this. We don't need shared libraries. We're not going to do Python, and can be that. Rest, I think, is fine. Okay, let's see if that shows. So here, CMake will try and find everything that LAMMPS needs to compile its thing. So we can have a look. The text, the C++ compiler, it finds Git, it finds CMake, it finds MPI, and you can see this is a very good way of making sure that LAMMPS is finding everything that it needs. It's finding BLAS from the libsci Python. It doesn't find FFmpeg because it's not available on LAMMPS. It finds FFTW3 version 3.3.10. It's downloading something for I forget which package it is, but one of them downloads something. It finds a Fortran compiler, and then it lists at the end of it what tools and libraries have been found and used, and then it prints the configuration of stuff that it's going to use, what system it is, where it's going to install, and all the packages and stuff like that. So you can have a look at that before you commit to compiling. So the next step is to, so I can show you that. CMake has created a bunch of files here. The most important pre-copying some stuff that's going to be needed. So the next step is to make the -j flag here is just so that you can use more than one core at a time instead of taking ages. It is quite quick. I think it takes a few minutes, but nothing too much. And then the last steps. Then the last step here, after make install, copies the files that were created to that install directory that you set up. And then if you're doing the Python version, you also want to do this so that it installs the Python wheel that it creates. Some of this is explained here. I think I went into a little bit more detail here. And then if you create your own, you will want to add your install folder to your path, or share that with your colleagues. If you want to share with your colleagues, you'll need to put it someplace that is shared between your project, for example, in /work/project_ID/project_ID/shared. If you want to share with people from other projects, you'll need to do /work/project_ID/shared. So there are two levels: sharing between your project and sharing with people outside. This is taking a bit, but we'll see. If we do module show lamps, again, you'll see that basically this is the things you need to do after you compile LAMMPS yourself if you want to use LAMMPS. So on your Slurm script, you'll need to load CPE and FFTW. You'll then want to export your path to include all of these. For LAMPS, it is useful to set the Slurm CPU frequency to the maximum. By default, I believe this has been changed to 2.0. And then you want to change your path to include the bin folder and your manual if you want to have a look at manual. The commands aren't exactly these. It would be something like export, for example, for the path. Export path equals you want to do something like that, so that your path the location of LAMPS gets prepended to where path actually to the entire path. Your path variable, if you don't know, is all the locations where binaries can be found. So when you do which LAMPS, it can tell you that it has found no LAMPS in any of the locations in path. If you compare all of these folders to all of those, they are the same. But if you export this, no, that way. The echo path, you should see that the first one is the location of the LAMPS binary, and then if you do which LAMPS, it now finds LAMPS inside that folder. This is almost done. So after these, like I said, is make install. That takes another 30 seconds or so. Then you can use the binary. Okay, I think I missed a couple questions here while I was talking. Thomas, okay. Maybe a naive question regarding the rerun. When we calculate the radius of generation, we use the partition to do all the calculations all at once. As far as I understand, the replica exchange was done before, and therefore the same tool is used for two different tasks. Am I right or not? Yes. The exchange was done before. Here, there will be no temperature exchange between each replica, but you'll see you can still run the same, all the 10 at the same time, one on each core. So that's basically why we're doing it. And because the world variables are the same, we can just reuse that. So because basically we copied the input file and modified it slightly so that it was okay. Anyone that's interested in compiling, did I miss anything that you're curious? Is there anything you want me to go into more detail? I think Robin, was it? Okay, good. So if you have any trouble installing your own version of LAMPS on ARCHER2, or even just a slightly different one with different packages, you can always email support or from the web page. There's a form. It will come to one of the CSE members, and we can definitely have a look and try and help you with that. Sometimes there's stuff that details about the ARCHER2 software stack that can escape someone that's not intimately familiar with it. So don't worry if at first you're failing because you're missing a library somewhere or you're getting a weird error. Right, so feel like I'm about to lose my voice. It's not good. You can have a look at the Python implementation. So I don't have, oh, I do have LAMMPS, but I'm going to need LAMMPS Python. There we go. Now we have both loaded. And it might be good to know that this LAMMPS Python implementation, it is literally just a wrapper, a Python wrapper around the same LAMMPS binary files. So the Python script will just call the compiled LAMMPS. So in terms of performance, as long as you're not doing a lot of stuff in Python, you shouldn't notice a lot of difference. That said, if you're trying to distribute one LAMMPS process across several nodes, you might get a little bit of a hit in startup time, but then during the calculation, it should be fine. We've not had a lot of people using these yet, so we've not had a lot of examples of, especially not very large systems being run with this. But as far as we could tell, the performance of the actual simulation is very similar to just the plain C++ one. Now, why might you want to run, to go into the complication of running LAMMPS with Python? For most things, you shouldn't. But if you're doing anything that you're trying to do any kind of flow control, depending on what the simulation is doing, or if you want, I don't know, start splitting polymers or adding stuff, you might find that the syntax of Python is much easier than the syntax of the LAMMPS input file. So there's lots of things that you might think, well, this would be so much easier with using Python. And it's in that case that you might give this a go. And if you have good or bad experiences, please do let us know. We're interested in what's happening with this. So it is, to run on a single core, it is as simple as import LAMMPS, create a LAMMPS object, read a file, and run it. That is honestly that easy. If you already have these, you might as well just run the input file directly. The exercise here that we can have a go now, we actually have something that's and I can show you the input as well. So on this Python file, we are changing the name of the log depending on a for loop here. We loop this 5 times. We have a different log. We change the cutoff and the pair interactions, and then we run 100,000 times on for each of these. That will create 5 logs with 5 different cutoffs on the pair interactions. You might see here these 3 lines that are commented. It used to be the case that you needed to explicitly import MPI for Pi if you wanted to run LAMMPS with more than one core. As far as I can tell, these changed on a recent version of LAMMPS, and I believe that the manual might not have been updated, or there's a weird interaction between the ARCHER2 Python implementation that is just calling MPI for Pi directly. I've not been able to determine which one of those options is. But running it without MPI4Pi on ARCHER2 works, you might find that on a different system, you might need to explicitly import MPI from MPI4Pi and initialize the communications and finalize the communications at the end of your script. So that's why I left the lines there, so that it doesn't come as a surprise. So the other change you need to do is, instead of calling on your slump file, instead of calling LMP-I, you call Python and give it the Python script, and then the Python script will read the input file. So if we do this, we should get this running. Please go ahead and try and run this, and then we can have a go at the exercise here of changing the temperature rather than changing the cutoff. As you can see, creates the 5 log files. And you'll see if you open the other ones, the pair coefficient will be different for each of them. And then, of course, total energy will be different depending on the cutoff. And this is the kind of thing that will be easier to do with a Python script rather than with LAMMPS. So if you're trying to change, if you're trying to run the same system at several temperatures, or if you're doing some shearing and trying to do different sliding speeds, it might be easier to do this way rather than having to figure out the variables in the LAMMPS input file. Now, once you run the default file with try and change the temperature, although I believe this is incorrect because those are unified units. So I think you can change by 0.25. Yeah, so these are not Kelvin, these are Lennard-Jones units. So instead of 25, change it by 0.25 here. Instead of 25, 0.25 on, it would be this fixed line. I think 10 minutes should probably be enough of that. So, and help us to, we'll continue with the last bit, which will be GPU acceleration. So, does anyone have a solution for this exercise they'd be willing to share? Has anyone managed to do it? And if not, what is blocking you? So on the temperature, so I want to change this fix. And because we want constant temperature, you'll want to increase these two. By changing these two. Sorry. I mean, it wasn't constant temperature, my bad, my mistake. We want an increase of 0.25, so we want this one to be on the first run 1, and you want this one to be 1.25. And on subsequent loops, you want both of them to increase 0.25, basically. So you want this one to start at 0.25 and that one to start to be 1.5. Just another few minutes to have a go, or would you like the solution? Yep, 2 different variables is fine. With different looping might be harder, because you'd want 2 different variables. You can make them depend on the same loop index, basically. No, you want them to increase simultaneously. So the idea here is to start with, so the first simulation increases your temperature from 1 to 1.25, then the second loop starts at 1.25 and increases it to 1.5, then the third loop 1.5 to 1.75, and so on. So you want a continuous increase here. I mean, for this exercise, for other purposes, it might be something different. You could just need the one variable then. It depends on how you implement it. There's many different ways. But if you have a solution, please share it. The either pound if that's easier. I don't know. Section here. Sounds like you're defining a string rather than a number, and you'll probably also need to cut off twice because you have 2 spaces for variables, and then you'll need them both. Okay. I can show you the solution I propose. See if it's any close, and if it's very different, we can have a chat at why during the break, which is coming in 10 minutes or so. No, this is my proposed solution. Again, there will be other different ways of doing it. First of all, I'm putting the pair coefficient command outside of the loop because it won't change. So we'll keep it the same, so you don't need to make it different. You could just add it to the input file instead. Both would work. And then again, a range of 5. So I will be 0 to 4. Don't forget that Python indexes to 0. And then I create 2 temperatures. Basically, temperature start, temperature finish. The first one starts at 1 and then increases by 2.5 each range. Again, as I starts at 0 on the first loop, it will start at 1. And then temperature 2 will always be 0.25 higher than temp 1. I'm naming the logs differently than the previous one, just to keep them separate. So log.temp.temp1, this will be 1.0000 whatever for the first one, and then we'll increase by 0.25 for each. And then this won't do nothing on the first time, but you might want to include it so that it removes this fix from the previous loop and creates a new fix. And then, yeah, the 2 variables like you had, Xenia, and then the 2 temperatures. And then again, run. And I was running this while you were doing your exercise. And as you can see here, we've got 5 different temperature logs, all starting at the temperature here in the name. So this one will go from 2.0 to 2.25. If there's any questions about these or any of the other sessions, happy to answer. Otherwise, you can have a break. My voice needs a little bit of a break. And then on the last bit of the of this course today, I'll show you a little bit about using GPUs. Unfortunately, we'll have to be on Cirrus, not on ARCHER2. And then we'll finish this course. So if there's any questions, feel free. Otherwise, I propose we continue in 20 minutes, so at 3 UK time. So Andres is asking if there's any different on doing these modifications on the input file through Python LAMMPS instead of using bash on the submit file. If you did this using bash on the submit file, you would have 5 different. You'd have to have 5 different srun commands basically, and each of those comes with a little bit of an overhead. It's not much, but a little bit of an overhead. So there would be technically 5 different LAMMPS runs rather than one continuous one that just changes. So this is the equivalent of having an input file, a LAMMPS input file with 5 different runs with changing those fixes in between the runs. If you use bash to change those, will be slightly different than this. I think it's just easier for some people that already know Python and don't know bash. I think it's very common on the scientific academic community that people are much more comfortable with Python than with bash. So it's just an option. Okay, a little bit past 3, sorry for that, but we can do the last bit. I said I would show you some GPU acceleration. I'm afraid I haven't written the course material for this yet, but I will, and I will add it to the Git repo, hopefully still this week. But I'll show you on Cirrus how you could run using the GPU's accelerator. So I'm using here the same ethanol system that we've used on exercise 1, I think it was. The only difference is that, well, besides not being able to use the fixed balance command, is that you need to tell LAMMPS to use the GPU. So here, package GPU and how many? 1, and if you see here on these commented bits, I have 2 and 4. Oh, sorry. Yeah, I should be sharing. I'm not. I'll fix that. I'll restart this. Okay, so once again, I'm using the ethanol system, and on the slurm file, the difference here is you need to tell LAMMPS to use the package GPU and how many, and then this is suffix GPU. This appends GPU to any of the commands that can be run on GPU. It's just an easy way. You could just do it on an input file, but this is just an easy way to add them to all of them. Other differences. So this is command for 1 GPU, 2, 4. We'll be running. I'll be running this on Cirrus. Other differences is here the module on Cirrus. You'll need to tell it to use one of the LAMMPS modules that was compiled with CUDA. I'm using a different account here because it's not the training account. And on Cirrus, you need to tell it how many GPUs to use. And this is done by using these -gres GPU. If you change down here to 2 or 4, you also need to change this one up top. And this is the number of GPUs per node. So if you go, if you want, there are 4 GPUs per node on Cirrus. If you want more than that, you keep that on 4, and you add you increase the number of nodes there to 2 or 3 or 4, whatever you want. A little bit of something that's also slightly different here, but this is due to the way that Slurm works on Cirrus. It might be different on other systems. Is that to pass the number of MPI tasks to LAMMPS, we need to have these environmental variable, because if you try and do it directly, Slurm will complain. So this is a bit of a workaround to that. Each GPU node on Cirrus has 40 CPU cores, and with each GPU that you request, you get 10 of those cores. So if you don't do this, if you run, try and run LAMMPS that way, it only uses one of the 10 cores that you're allowed. So you're losing a little bit of performance that way. Well, depending on your system, but you'll probably be losing a little bit of performance that way. So we can have a go at this. It's the same way to start it, just as batch as run. And here I'm using the short queue, so I should be able to submit 2 of them at the same time, but only one of them will run. So if you have a look here, one of them is running, the other one will only start to run when my first one is finished. And the reason here is QoS max jobs per user. So you're only allowed 2 jobs in the queue, only one of which will be running, but these are a couple of minutes, so it shouldn't take too long. And then we can take a look. Most of the output is the same. There is a little bit of extra information at the end about how much memory GPU VRAM is used. Does anyone have any particular question about GPU simulations, or you're just interested to see how one is run? While we wait for this to finish, I could answer any questions. In the meantime, I can edit this again. Oh, I missed that one. Okay, need to cancel that one. I see your question, Andres. I'll get to that in a sec. Okay. So the LAMMPS code doesn't need to be adapted to GPU. In 90% or more of the cases, no. Just adding that -sf, that means suffix, that will automatically add /GPU to any of the commands that where that's available. So let's see if I can bring it here. Any of the pair styles. Sorry, it wouldn't be the pair styles, it would be the fixes. Yeah. Don't remember where the entire list was, but maybe on the package. If you come here, it will it gives you that explanation. The -fx GPU suffix just adds GPU to everything that allows it to run with GPU. So, oh yeah, it was the pair styles. No, I couldn't find any. But yeah, so any pair style or any command basically that has a /GPU version, if you do this -sf GPU, you will get that added automatically. And again, the package GPU and how many GPUs you want to run on. So it is fairly easy. There are still things that you can't do using a GPU. Off the top of my head, I think non-orthogonal boxes might still be an issue. But every new version of LAMMPS, they add stuff to the GPU accelerator packages. So that knowledge might be wrong. the better way is to try. And if it complains that it can't do it on GPU, then you know it can't do it. But most of the regular stuff should be available on a GPU package. Some of the user created packages might not be accelerated, but I think some of them are. And once we have some more information on the GPU nodes on ARCHER2, we'll be adding some information on our documentation as well. So once that's set up, you can have a look there. Let's see if this is done. Should be. So we can have a look. Log 1. Really? Interesting. 2. So this is with one GPU, and we should be able to see that. Yep. So device 0, Tesla V100, which is the GPUs on series, and then it tells you which CPU cores it is assigning to device 0. In this case, all 10 cores are being assigned there. Then you have the same neighbor and stuff information as you had on the CPU version of the code. But then you also get device information for the GPU stuff. So you can have a look at how much memory per process you're using a lot of timing information as well. So how much, if you're losing a lot of time on data transfer between the CPU and the GPU, for example, might be something that you need to be on the lookout for. And so this would be the stats at the end. Got some idle time on the CPU. So the system is not very big, so I'm not surprised. So the CPU was waiting for a little bit of time for the GPU to calculate stuff. And something you might, and that's just for case-based, that's for everything, I think. And something that you might want to keep an eye out is your max memory, because unless they've changed it on the last few versions, if your system occupies more memory than you have VRAM in the GPU, it will just crash without saying why. So if you're seeing weird crashes, that might be the reason. So this took 1 minute 26. I don't expect that by using more GPUs in this case, we'll see much improvement. Okay, that's a little bit. So 4 times the GPU, and we shave like 20 seconds. Like I said, this is a very small system, so I'm not surprised that communication over hands will be a little bit on the high side, as you can see here, 14%. But then this was just an example of this. Does anyone else have any other GPU-related questions, or even from the stuff we were doing before? Let me know. Otherwise, I think this is the end of the course. I'd like to thank everyone for coming. A little bit on what other things you could have a look at. The LAMMPS manual, it is incredible. It is incredibly detailed, and it has a lot of information and on all the packages and commands. The how-to section here has a lot of tutorials, how to do things from the basics to the more complicated stuff, including stuff with packages and even how to compile LAMMPS if you're having some trouble with that. I think I mentioned this one before, but the LAMMPS mailing list. If you have a question and our documentation or the LAMMPS documentation doesn't make it clear, search here. Probably someone has already asked and that question has been answered, probably by Axel, one of the main developers of LAMMPS, if not from someone in the community. And the LAMMPS exam scripts that come with on the Git repository when you download LAMMPS, there are several dozens of directories, which each of them with several different examples on very different systems and different applications and processes. So have a look at all of these things. if you're trying to do something that you're not familiar with, and you might find an example here, they are usually very simple and very well commented. And it's usually a good place to start with a script that you can edit for your own purposes. On ARCHER2, your TA132 account will remain active for, I think, 2 or 3 months. There is a little bit of budget on this account. You are welcome to use it, to test your stuff, to take the data that you created today out. The GitHub will stay on. We don't delete those. And that will be available all the time. Very soon, the recordings from today will be available online, as well as are pretty much all of our training courses, at least the ones that are online. If you come to past course materials, and you'll see that a vast majority of the online ones have the video symbol here, and if you click that, it'll take you directly to the video recordings and all the material you can then get. For example, introduction for soft developers, you'll have the course material here, as well as the videos down here. So if there's any of our vast amount of courses that you want to have a look at, but we're not offering it soon, this is a good way of having a look at. And finally, if you could please provide us with some feedback. I'll paste the link in chat, but it's also on the training page. It's also here at the bottom here, feedback. If you could please fill that in. If there's stuff you would like to see on the next version of this course, it really helps us. And finally, I will try and add. I'll try to write a little bit of the GPU stuff on the repository and upload it to the course notes, so it should show up here on this page as an episode after Python, hopefully this week, if not early next week. I think that's it. If there's no other questions, I will stop the recording. Again, thank you, everyone. Thank you for coming. And if you have any questions about ARCHER2, our support is always happy to answer their email. If the question is related to the training course, please mention it, and that will come directly to me. All right. Thanks, everyone. Goodbye.